well, thank you. On behalf of the Kepler Project, I want to thank the AAS for organizing this event. Today, the Kepler Project is announcing 461 new Kepler planet candidates. For those of you who are unfamiliar with Kepler in the audience, Kepler is a NASA space mission which is managed by NASA Ames, and it's finding these planets in stars outside the solar system using the transit technique. The main goal of Kepler is to find planets in the habitable zone and characterize the population of these kinds of Earth-sized planets. So as a stepping stone towards this goal, we've announcing 461 new planets, and what I'm going to do is take a little bit step backwards in time to 2 years ago to put these new results into context. So here's the planet candidate sample that we had 2 years ago. We had around 12,000 planet candidate objects. Here I'm showing orbital period versus planet size. A year later, we added a significant number of new objects. Definitely, we saw the trend of huge numbers of very small planets, like super Earth, twice the size of Earth and smaller. And now, with this new data set, we've analyzed 22 months worth of Kepler data, and we're adding 461 new objects. This brings the total count of planet candidates up to 2,740 found by Kepler. Now in this figure, Kepler is most interested in the things on the long orbital periods and the small planet sizes. Those are the things in the lower right corner here. As we get more data, we'll get more sensitivity towards those parameters. So to summarize, we have 461 new planet candidates. In the rest of the talk, I want to demonstrate these three main points. What we see in this new sample of object is the growth of new objects is predominantly in the super Earth to Earth-size objects. We really increase the number of those objects that are now planet candidates with Kepler. Second of all, we are continuing the trend of finding these planets in multiple planet systems. These are stars that have more than one planet in them. These systems are extremely exciting because you can do very interesting astrophysics. You can learn about planet formation when you study the dynamical interactions between these planets in these multiple planet systems. And finally, we'll focus on these habitable zone planets. The habitable zone is where liquid water can hopefully sustain life-bearing organisms, and so we're trying to find these things. You need very specific conditions to have liquid water. You can't have your planet too close to your star to be too hot, and it can't be too far away for the planet conditions to be too cold to support liquid water. So we're trying to find these planets in this very specific zone, this habitable zone. So to demonstrate the first point, here now is a breakdown of the cumulative total planet candidates found by Kepler. The histograms are bins of planet size. The leftmost bin is one of the more interesting ones. We now have 351 Earth size, which is 1.2 Earth radii and below. Now the percentage there is the percentage increase from our sample from a year ago. So you can see we grew the number of Earth-sized objects by 43% from a year ago. This is expected as the data from Kepler grows in size. We're able to be more sensitive to these very much smaller signals. Again, we saw additional increases in the super Earth size. These are things that are twice the size of Earth and smaller. So here now I'm demonstrating the multiple planet systems that we have. The different rows are the number of planets that Kepler has observed in these systems. Starting at the top are the planet systems with only one planet, down to 2, 3, 4, 5, and 6. The column on the left is the planet sample candidate from a year ago. And now in 2013, with this cumulative result, are the planet candidate totals in these multiple planet systems. So we've added systems that now have 5 observed planets in them, is up to 11. We still have only a single 6-planet system right now, but growths across all of these categories with this new catalog. And the final point I'd like to illustrate are these new habitable zone systems. The new systems we're announcing are these points, the yellow points here. And in this figure, we're interested in the things down in the lower left corner of this diagram. This green strip there is this habitable zone that has a very specific conditions that can possibly have liquid water. So what I'm going to do is zoom in on this habitable zone so we can look at these most interesting candidates. Here, our new candidates are marked in yellow. And what I want to bring attention to is, in addition to the large number of yellow objects smaller than Neptune. I want to bring your attention to just 4 of these new habitable zone candidates found by Kepler. These all 4 have estimated radii to be less than twice the size of Earth. In particular, one of these is around a solar-like star. The other 3 are around stars that are much cooler than the Sun. But we're very interested in finding planets around stars like our Sun, like we live around here in our solar system. This one is a radius of 1.5 Earth radii estimate, has an orbital period of 242 days around a solar-type star. So that one in particular is very interesting. So to summarize, we're announcing today 461 new planet candidates. The cumulative total now with Kepler is 2,740 across all the different planet candidate samples we've announced. The largest population increases are in the small planets, the Earth size and super Earth size. We really increased the fractional numbers of those. The next bullet talks about the multiple planet candidates. We've increased just the number of multiple systems. But we've also continued the trend that multiple planet systems are very common. If you're a planet that Kepler has observed, you're 43% likely chance to have another planet in the same system. That's been observed by Kepler. Finally, we want to focus on these 4 new candidates in the habitable zone that are less than twice the size of Earth. And one of these is particularly interesting because it orbits a sun like our star. The planet candidate table for these that I've talked about today are available at the NASA Extrasolar Planet Archive at the URL listed there. Thank you.
Hello, I'm François Fresson. I work at the Harvard-Smithsonian Center for Astrophysics, and I want to report on a very exciting result we got with a collaboration with other people working for the Kepler mission at the NASA Ames Research Center. And we've been able to work on the candidate catalog and find what is the underlying population of planets. And the headline of our work is we found that at least 1 in 6 stars has an Earth-sized planet. So we worked on the February 2012 catalog, so the previous catalog, and we know that the list of Kepler candidates contains most of the knowledge about exoplanets. And in fact, we still have difficulties to digest it, these paradigm shifts that occurred when the candidate catalogs were released. And another reason that they're tough to digest is because there's a few issues if you want to extract what is a chance for a star to hold a planetary system just from these histograms. First, it's the fact that the catalog is not complete. For every planet that Kepler sees transiting, there's dozens that are not transiting because they are not well aligned with the observer. And also, even if Kepler is extremely accurate, he's not able to find out all transiting systems, especially the smaller planets transiting the larger stars. And the second issue that is also difficult to disentangle is the fact that the catalog is not pure. Despite all the efforts that are led by the vetting procedures that leads to the candidate catalogs, there are false positives among the small dots that constitute the histograms. There are some of those that are not due to planets transiting their host stars. So in order to correct for the incompleteness, what we do is we've been using the actual detection level of a list of more than 2,000 candidates to find out what is the actual detection recovery rate of Kepler. And to correct for the impurity, we had to tackle the issue of these false positives. It's well known that an observed periodic transit signal could be due to a transiting planet or any kind of astrophysical configurations of 2 eclipsing objects, eclipsing each other, in the same pixels as the stars we're observing. And what we've been doing is we've been doing a simulation of the Kepler survey, focusing on all these false positives, and trying to take into account all configurations we can think of. And we found out that altogether, these configurations could only account for 9.5% of the huge number of Kepler candidates. All the rest, even if it's very difficult to check which ones, are bona fide planets. And here is our most important results. This is the occurrence of planets, so the fraction of stars that have at least one planet. The numbers for the large Neptunes and the gas giants on the right were fairly known already. But there's a dramatic increase in the occurrence of planets when you check for the small Neptunes column. And we were able to provide what could be considered as the first robust estimate of the occurrence of super-Earths and Earth-sized planets, the most important result of this presentation. So we were only able to provide it for the short periods, simply because there's not enough candidates at longer orbital periods. But we can say that 1 in 6 stars has an Earth-sized planet within the orbit of Mercury. So why can't we provide an estimate in the habitable zone? Where do we fail? We don't. It's simply nature is such that in order to catch several transits, like 3, 4, 5 transits of an Earth analog orbiting in 365 days, you have to wait for 1 more year to get another transit. So it's simply too early to call. We only have 30% of the whole Kepler data in. Kepler is still observing. We'll be able to make a statement, but it's right now too early to call. But there's another very important result that we get along these lines. So 70% stars have an Earth-sized planet only within 85 days. But if we add the larger planets, and if we go up to longer periods for which we can make estimates, we already know that 70% of stars have a planet of any kind. And we know it's not complete for the Earth and super-Earth, but 70%. And if you make very reasonable extrapolations on the current Kepler observations and also results from other detection techniques, it's very easy to claim something like that is very close to 90%. So think about it. Almost all sun-like stars have a planetary system. If you randomly travel to a star, it will have a planet. We can't say if it will be welcoming, but it will have a planet. But you're going to tell me, we've only been studying the previous candidate catalog. So what about the ones that has just been released and I'm kind of discovering at the same time as you do? So I've only been able to run very preliminary tests. And in fact, if I apply the occurrence rates I determined, and if I assume that the observations lasted 22 months instead of 16, I was expecting to find only 260 new candidates. But Chris just reported that there were 460. So what's wrong? Are the numbers I presented wrong? No, it's the model of the detection of Kepler that improved. So the numbers still hold, and it's Kepler is doing better at finding smaller objects. And another very interesting side results we had is it was previously thought that small planets were way more common orbiting small stars. And what we found out is the fact that the occurrence of small planets orbiting large stars was underestimated. And so right now the two numbers are quite close from each other. And in fact, the results of Kepler can be explained with planets equally common orbiting the different stellar types. And I think my main headlines are very easy to remember. First of all, you have to look up and look down. So if you look down, you'll see that we're standing on a planet, and these kind of rocky objects are everywhere. And the thing on that line is, if you look up on a starry night, each star you're looking at, almost each one of them has a planetary system. Thank you very much.